For today's warm-up, who can tell me what is happening to this tank of water? What is happening? Cam?
I think it's decreasing.
Okay. What's it starting at?
80.
Starting at 80. And then, Cam, can you tell me how it's decreasing?
I think it's decreasing by 2.5 every minute.
Yeah, 2.5 liters every minute. So again, we can take our function and we can use our function knowing that this is a tank and say, hey, our tank's starting at 80 and we're losing 2.5 liters per minute. So that's pretty cool. What does W of T represent in our function? Right here. Who can tell me what that stands for? W of T. Vinny?
Water and time, right?
W of T is all just one thing. It's a label. It means, right? W's not a variable here. It's a label.
It means the amount of water.
Yeah, amount of water in tank. Again, it's tough because we're switching here to function notation. We haven't touched function notation in a few days, right? So W is not a variable. W of T is function notation for if time goes in. W of T, the thing that comes out is how much water is left in the tank. And then the T. Who can tell me what that's standing for, the T in our function? Yeah, Sean?
How much liters are decreasing every minute?
So that's the 2.5 portion. Right?
How much time?
T is time in minutes, right? So we've got amount of water in liters and the amount of time in minutes. So if I'm going to label my X and Y axis, I got time down here in minutes, and I've got volume here in liters. So where am I starting again? At 0 time?
80.
I'm starting at 80. So I got a nice y-intercept there. And then the next piece is I want an x-intercept, actually. So how long is it going to take for this thing to be empty, and how do you know? What do you got, Brendan?
I got 32.
Yeah, me too. How'd you know that?
80 divided by 2.5 is 32.
So 80 divided by 2.5. So it's at 80. It's losing 2.5 a minute. So you divide it out, take 32 of those. And then here's our function right there. 80. Now, why don't I need to go into negatives? Because it doesn't make sense. You can't get less than 0.
Correct.
Ooh, black matter. But dark matter, whatever, maybe. I don't know. But you can't get less than 0. So this is our function. Back up at our original function. W of T, is that the input or output? Yeah, right here's our input. No, W of T. Output. What was T? Input. Time goes in, liters comes out. Time goes in, liters comes out. All right? All right. Everybody go with this because we have to be good with this to do the next thing. Output is W of T. Time goes in, volume comes out. W of T is the function of T, which is volume. So just be ready. We're gonna mess with function notation more today than we have been. So far with our inverse functions, we haven't messed with function notation. It's not different. Just instead of like y, we have f of x or something like that. No different. Remember, it's just a label. W is not a variable here. Now with your partner, we're still working in our same tank premise. You're going to answer some questions related to minutes and liters. You're going to try to work on getting an inverse function. By the way, earlier today we had some classes get an inverse function that was wrong, but we could use their wrong answer to mold success, right? So get it wrong if you need to get it wrong. And then we're going to actually compare these graphs on Desmos. And you'll see why. It's going to be pretty cool. Hopefully we create this really good big idea you can use for inverse functions. So I'm going to give you about 7 minutes with your partner here, I think, to get after this. The one that's going to take some time is the inverse function one, maybe. The other ones I think will go pretty quick for you. Who can help me figure out how to find out how much water will be there after 13 minutes? How I'm going to use that information with what I've got? All right, Meredith. Yeah. So the function of 30 means I'm going to start with 80, take 2.5 off for 13 minutes. So W of 13, or the function of 13, is, what'd you get? 47.5. So in context, what this means is, after 13 minutes, input 13, the output is 47.5 liters. We good there? So this function, W of t equals 80 minus 2.5t, is really good if you know the time, right? But what are we given for number 2? We're given liters. So we have 2 options here. Option 1, which is kind of trying to get you to do, I think, is liters the output or the input of our function? Output. So you'd have to say 5 equals 80 minus 2.5t. So that's how we can get it into our function, right? And then what would we have to do to isolate t? Subtract 80. Then do what?
Divided by 2.5.
Negative 2.5. But I'm going to propose we jump down to number 4 and find this inverse right now. So to find the inverse, I'm going to start with my W of t equals 80 minus 2.5t. And like you guys just said, to find t on number 2, the first thing we would do is subtract 80. Everybody follows? If you don't have this, you need to be having it.
But this isn't a variable, it's just a...
I just subtracted
Yeah, just watch.
5.
So that's where I'm at right now. The function of t minus 80 equals negative 2.5 times the time. So how do I get rid of the negative 2.5? Divide by, which is exactly what we talked about doing from the function up top. So let's get that. We got W of t. I'm just going to write the inverse here because I have space. I can get time if I know the output liters minus 80 divided by negative 2.5. There's also an equivalent one here where we could do 80 minus W of t over 2.5. But again, here's the minus 80 right here. See that minus 80? Here's your divided by negative 2.5 right there. So what is the time we ended up with for 5 liters? I can take 5 liters, smack it into there, and we get 30 minutes. So let's make a point. Let's make a point here. If I look at this function here, okay, the input or the input time would be 30 minutes, and the output liters would have been 5 for my original function. My new function right here, what did I input? I inputted 5 and pumped out 30. What do you notice about my ordered pairs with my original and my inverse function? They're just swapped. That's going to be true for everything on the whole graph, right? Because my equations are equivalent, right? We do the same thing to both sides, but our input and output flip. So guess what's going to flip in our ordered pairs? The input and output. So that's what I'm going to write for the graphs. We'll look at it too. Input and output are flipped. That's why it's called inverse, right? It's called inverse. So I'm going to work on getting that up on a Desmos for us to take a look at, just so you can like do more than just take my word from this one example. Because sometimes in math we can find something that works once, but it only works in that way, right? It doesn't work in all ways. So let's take a look. So let's take a look at the Desmos graph. So the original had a y-intercept of 0.80. So what would you expect the inverse of that to be? If I flip 0.80, check it out. 80, 0. Okay? Let's just check a random point, like at 20 minutes. 20, 30 means at 20 minutes there was 30 gallons left on the original. So the inverse would mean 30, 20. Let's check it out. Come on, Desmos. There it is. So it's true. For all points on both functions, the inverse pumps out. XY becomes YX because the input becomes the output becomes the input. We swap independent variables. Makes sense. It's the inverse, right? Same equation, we flip variables. Cool. Here's our last thing we're going to look at with inverse functions. We're looking at phones in homes. We've kind of looked at this a little before. This is the percentage of homes that only have cell phones. Okay, that means no home phone. What do you notice about our dots here? If we connect them, what are you noticing? They trend up. Is it linear?
No.
It is not a perfect line. So we can't associate a function to this, like a linear function to this, because it's not a line. So what we're going to do is create what we're going to call a line of best fit, which means a line that is like pretty good at saying what's happening here. A linear model. You've seen that word before, linear model. So it's not perfectly, and like on a test, we could all have lines that are a little different. So I'm looking at making a straight line on here, and I'm thinking here to here like this. I'm thinking that line is the one I'm going to use. So do you see how I have like a straight line that like pretty much goes with my data really well? Some people first hour just use these first 2 points. Look at the line, what happens if you just use the first 2 points. Is that second line a good line that explains the data? No, but the first one is, it's pretty close. So you're going to lay down a line that you think is pretty good on there. All right? A line of best fit, also known as a linear model. Then you're going to work on giving a function for this line. Now, it's been a minute since we've written equations for lines. What are the only 2 pieces of information you need to write the equation of a line? Give me one, Ivy.
The y-intercept.
Okay, so B, which is y-intercept, right? What's the other thing you need? Ava? Slope, which is M. And so we're looking at slope-intercept form. This one asks for in function notation. So since it's percentage, I would use this general form. P of x equals mx plus b. Okay? So you need to find slope and y-intercept for your line of best fit. It might end up being a little different than mine, but we're going to be in the same ballpark, all right? So you and your partner are going to work on that right now. So when I went after getting my slope and y-intercept, I grabbed this point here, which I said was like 0, 3.5. And I used this point here, which I said was like 1, 7. So those were my 2 reference points I chose to use. Which what this would give me is a slope of, I went up 3.5 over an interval of 1. So 3.5x, that'd be my slope, 3.5. And then mine starting at 3.5. So this is the line I got. Anybody get a different line? I know you did. Ivy, what'd you get?
I had my y-intercept at 4.
Yep.
And then the slope was, I used the first dot and then like the dot at 4, like where the x is 4.
Okay, so what'd you get for a slope?
So 3.375x.
That could kind of work. I'd be careful using these 2 lines because then that makes something like that. You're saying you use this dot and this dot?
No, I used the first dot and then the 4th dot, or the 5th dot.
Oh, because you saw like it was pretty close? Okay, yeah. So again, that's ballpark to mine, right? What, is there another one out there that we got? 4x plus 4. 4.5 for the slope. Okay. Yeah, they're ballpark-ish, right? 3.8, yeah. I had a 3.6 earlier today for slope. So we did it. This is our line of best fit right here. P of x equals 3.5x plus 3.5 or ballpark, right? All right, let's look at the next slide here. So I'm gonna throw it down in the bottom corner here for us to just look at. Oh, that didn't work. Wow. It's because I'm doing Oh wow.
Yep, you need a new iPad.
Yeah, need a new iPad. Okay, I'm back. It's because I wasn't on annotation mode. Okay, I got this. So there's I'm going to throw the function down in the corner. So P of 6, in context, what is that meaning? P of 6. Meredith?
What was the percentage 6 years after?
Yeah, percentage 6 years after. So I'm looking for percentage, which is my x in this case. In this, it's using t for time. We used x, it's all good. So that means it's increasing by 3.5 a year for 6 years, and it's starting at 3.5. So for mine, yours is going to be a little different maybe. I got 18 plus 3, 21 plus 2, 3, 21 plus 3.5 is 24.5. To explain what this means, I'm going to go down here where I have space. That means 6 years after, what was the reference here, 2004?
Yeah.
Which would put us in 2010. 24.5% of homes had no cell phones. Or only, I mean, had only cell phones. That's what that means in context. Now, If we have P of t equals 30, what does that mean in context? P of t equals 30. Kai, what does that mean in context? 30 years after? Okay, so up here, 6 was our years. Input 6 years. This one is saying I don't know. 30. So really what it's saying is after how many years will we be at 30%, right?
Yeah.
So I can put 30 in for P of t. But what have we been working on doing to like simplify this? The inverse. And the big reason is, look at number 4. If we start slapping a bunch of percentages in there, we'd have to do 2 steps of algebra each time. Where if we go after making the inverse, how many times do we have to do the 2-step algebra? 1 time. So let's do that. P of x equals 3.5x. I know there's a t in some of it. It's all good. So to get x alone, I would have subtract 3.5 from both sides. So 3.5x equals P of x minus 3.5. And then how do I undo times 3.5? Divide. So here's my function. X equals P of x minus 3.5 over 3.5. So just like here, you'd subtract 3.5, divide by 3.5. The inverse function just has that ready to go. So if we do that, let's do it with the inverse function. X equals 30% minus 3.5 over 3.5. I got something like 7 point something. Here, my calculator's right here. 26.5 divided by 3.5. 7.6-ish years. So again, big idea here. Again, what's going to happen to our inputs, outputs once we do the inverse? They're going to flip. XY is going to become YX. You'll actually use that in geometry when you're doing some translations too, which is kind of cool. And again, another big idea, the reason we want to is if we want to throw years in, we throw years into the original function. If we want to throw percentages in, we throw percentages into the inverse function. So that way we don't have to like solve for a variable over and over. It's actually, have you guys noticed a lot of things that we do in math is to help, once we base something on understanding, we make things more efficient. Have you guys noticed that? Now you can get real efficient. You ever see those like TikToks with like math hacks? But you'll never, they're based on understanding, most of them. But you'll never remember it because if it's not based on understanding, you just got to remember 5,000 math tricks. But if you got a math trick based on understanding, it's all there. So this can be a math hack, but it's based on the understanding that an inverse will change your input and output so that you don't have to solve for a variable every single time. You can just do it once.